We have covered several episodes about the Big Bang model before. We've discussed its origins, the various processes that occurred during its stages, including the debate about whose time describes the Big Bang era. In the episode about the first second of the Big Bang, we mentioned that after the inflationary expansion, the components speculated in the Big Bang theory began to decrease noticeably. This reduction was due to the fact that the energy of particles during this period had dropped to levels within the range of current high-energy physics experiments. Therefore, understanding what happened before inflation remains a challenge in modern science. It's even accurate to say that everything truly began after the period of inflation, which is what we refer to as the Big Bang. In essence, the Big Bang isn't a process of creation out of nothing. It is a way of tracing the evolution back to an extremely dense and hot initial state. If we attempt to go even further back, we encounter a mathematical singularity through general relativity, which lacks any physical meaning. Hence, the Big Bang theory shouldn't be considered as a theory of creation. Instead, it stands as an observed and widely accepted model for the evolution of the universe. Thus, while the phrase, "the universe was born from the Big Bang," is sometimes used, it's more accurate to say, the universe evolved through the process of the Big Bang. The emphasis lies on evolution, not birth. However, compared to today's refined Big Bang model, early theories had certain significant issues, including the horizon problem and the flatness problem. Today, we know that the observable universe has a radius of about 46.5 billion light-years. People often ask, isn't the age of the universe just 13.7 billion years? Why is the observable universe so much larger? The answer is rooted in cosmic expansion. As the universe expands, the distance traveled by photons lengthens, and not only that, the wavelength of the photons themselves stretches accordingly. Calculating from the degree of stretching of the cosmic microwave background radiation, CMB, photon wavelength, we estimate that the universe expanded by about a factor of 1,000 from that time to today. This implies that around the time of the decoupling, when the CMB was produced, the observable universe's radius was already around 100 million light-years. This leads us to a problem. Since the initial photons appeared during the lepton epoch a few seconds after the Big Bang, and it took about 380,000 years for the decoupling to occur and the CMB to form, photons could only travel a distance of 380,000 light-years in that time. Yet, the observable universe's radius was already around 100 million light-years. The particle horizon radius at that time was only a fraction of 38 100,000ths of the observable universe's radius, creating a significant mismatch. This is the horizon problem that early Big Bang models couldn't address. Here, horizon refers to the farthest distance that light could have traveled within the age of the universe, beyond which two regions are causally disconnected since the speed of light sets the limit for information exchange. The manifestation of this issue is seen in the uniformity of the cosmic microwave background radiation temperature, which is approximately 2.7 K today. On a macroscopic scale, it is almost isotropic, with variations of about 1 in 100,000. Two distant regions in today's universe were already beyond each other's horizon at 380,000 years, meaning that even for light, there wasn't enough time for mutual communication after that point. These regions are, in a sense, isolated from each other. The question arises, how did they achieve thermal equilibrium? This puzzle persisted until 1981 when Alan Guth proposed the theory of cosmic inflation. According to this theory, the universe underwent a rapid expansion at the very beginning, starting around 10 to the power of minus 36 seconds after the Big Bang and lasting about 10 to the power of minus 33 seconds. During this brief period, the universe expanded by a factor of 10 to the power of 26, stretching from an atomic scale to that of a whole galaxy. Why did inflation solve the thermal equilibrium problem? Before explaining that, let's introduce a concept, the Hubble radius. This doesn't denote the farthest distance observable through a Hubble telescope, but rather the region where the recessional velocity due to cosmic expansion doesn't exceed the speed of light. Unlike the observable universe, which includes all light that has reached an observer, the Hubble radius describes the region where the emitted light will eventually reach us. This means that objects within the Hubble radius still have a causal connection with us at present. Based on the Hubble radius, we can speculate that these initially disconnected regions before inflation were very close together, possibly within the Hubble radius. This proximity allowed sufficient time for energy transfer and the establishment of thermal equilibrium. Think of it like finding the same dinosaur fossil on two distant continents that were once connected. They might have drifted apart later due to continental drift. However, during the decoupling period, the Hubble radius was quite small and couldn't accommodate these regions. The solution to the horizon problem lies in whether the Hubble radius could have been smaller. In traditional Big Bang theory, the Hubble radius increases monotonically with time. Yet, in the inflation model, due to space's rapid expansion, while the speed of light remains constant, the distance photons can travel in the same time is reduced. This means the Hubble radius shrinks, which contradicts earlier assumptions. The flatness problem is comparatively easier to comprehend. We know that the universe today appears very flat from observations, with a curvature close to zero. Even if it has positive curvature like a sphere or negative curvature like a saddle, the radius is incredibly large, so large that the observed curvature is practically zero. Someone might question how the universe can still be flat despite the presence of so much matter that should curve spacetime. Note that this isn't about a single scale or level. Matter curves spacetime, refers to local situations. On the universal scale, general relativity doesn't provide a specific answer. It describes the evolution of curvature under different conditions. The universe's curvature is a value that changes over time, and theoretically, even a minuscule difference would lead to the amplification of curvature as the universe expands. However, after 13.7 billion years of expansion, the universe's curvature remains close to zero, implying that it started off extremely flat. Flat geometry is highly unstable for the universe, known as the flatness problem. The introduction of inflation allows a shift from the narrow path of going from 0 to 0 to a broader range where any initial value can evolve to 0. This rapid expansion of space smoothens out any curvature in the early universe. This means that the universe's flatness today isn't just an unlikely coincidence but rather an outcome brought about by inflation. Besides addressing the horizon and flatness problems, inflation also explains other phenomena. For instance, the absence of the predicted magnetic monopoles in modern particle physics finds an explanation in inflation. The rapid expansion diluted these particles to the extent that the observable universe might not have even one. In fact, Alan Guth initially proposed the inflation idea while considering this magnetic monopole problem. Lastly, it's important to note that there are various models of inflation, and inflation theory is the general term for these models. While these theories have resolved many issues in the traditional Big Bang model, contemporary cosmology still has gaps, such as the enigmatic dark matter and dark energy. We'll delve into the topic of dark energy, the other cloud looming on the horizon, in future discussions.